Hello friends, welcome back to my channel Path of Physics. In this video, we are going to discuss about solar constant, Angstrom's compensation pyrheliometer, determination of solar constant using Angstrom's compensation pyrheliometer, and temperature of sun. So let's get started. So first of all, what is solar constant? Solar constant is defined as the amount of solar radiation received per unit time by unit area of a perfectly black surface placed at the mean distance of the Earth from the Sun at right angles to the sun rays at noon in the absence of the atmosphere on mean solar day. What is mean distance of the Earth from the Sun? It is the average of perihelion and aphelion distance. What is perihelion? At January 3rd, the distance between Earth and the Sun will be at the minimum. So this phenomenon, this is called perihelion. And at July 4, the distance between Earth and Sun will be at the maximum. So this is called aphelion. Now, solar constant is measured using an instrument called pyrheliometer. There are different types of pyrheliometer: water stir pyrheliometer, water flow pyrheliometer, and Angstrom's compensation pyrheliometer. In this video, we are going to learn about Angstrom's compensation pyrheliometer. Angstrom's compensation pyrheliometer was designed by Knut Angstrom. It measures direct beam solar radiation, means the solar radiation coming directly from the sun. Its outer structure consists of a long hollow tube blackened inside. Then there is a protective lens. Then inside of the pyrheliometer, two identical blackened platinum strips are present, and a thermocouple module is also present. The protective lens is pointed to the sun to measure solar radiation. Now this is a simple picture of a pyrheliometer, Angstrom's pyrheliometer. Light rays falling in acceptance angle only are accepted by this pyrheliometer. This pyrheliometer consists of protective lens, hollow tube blackened inside, a black body, and a thermocouple module. Acceptance angle is close to 0 degrees. Generally, it is 5 degrees. This is made sure so that the lens can focus light into the black body. Okay. So this is another simple picture of what the inside of a pyrheliometer will look like. There is an aperture and there are two shutters to open and close the aperture. Then there are two blackened platinum strips. They are identical. Then a thermocouple is connected. I have not shown it in detail. Okay. So this is a simple picture. This is a long hollow tube, hollow blackened tube. There is a lens here. I have not shown it here. Then this is another simple picture of the internal circuitry in the pyrheliometer, the Angstrom's pyrheliometer. It consists of two blackened platinum strips, identical blackened platinum strips A and B. They are connected by a thermocouple. I already told what is a thermocouple in my previous video. Thermocouple is a sensor which measures temperature difference. It consists of two different metals. It's joined in such a way, joined in such a way that the thermocouple has two junctions. Then a galvanometer is connected in series. Now this A, the metal strip A is exposed to, in this figure, this A is exposed to solar radiation and B is shielded from solar radiation. Then this B is connected to voltmeter, ammeter, rheostat, battery and a switch. Okay, so these are the connections. Now A is exposed to solar radiation and B is shielded from the solar radiation. So when A is exposed to solar radiation, the thermocouple junction, both this A and the thermocouple junction connected to A becomes heated. So there will be a temperature difference between these two junctions, the junction connected to A and the junction connected to B. There will be a temperature difference. So there will be a current flow through this thermocouple and the galvanometer will show some deflection. Now to nullify this deflection, the switch here is closed. So current flows through this circuit. Current flows through B. B gets heated due to the electrical current, and we can adjust the value of the current using the rheostat here. Now the temperature difference, since B is getting heated, the temperature difference between this A and B becomes lesser and lesser. So the galvanometer's deflection will become lesser and lesser. Then eventually both A and B will reach the same temperature and the temperature difference will be 0. So the galvanometer deflection will be 0. That means there is no current flow. The net current flow will be 0. Okay, this is how the circuit works. I'll read it once more. A and B are two blackened platinum strips. They can act as black body. In the above figure, A is exposed to sun's radiation and B is shielded from the sun. A acts as a black body. See, A and B are both platinum strips, blackened platinum strips. So they can act as black body. That means they can absorb all the radiations, all the solar radiations falling on them. So in this figure, A acts as a black body and absorbs all radiation. So A's temperature rises. The thermocouple junction connected to A will also get heated. Due to the temperature difference between A and B, current flows and galvanometer shows deflection. To nullify this deflection, the switch is closed, current flows through B and B gets heated. Now rheostat is used to adjust the value of current. Now temperature difference between A and B becomes lesser and reaches 0. So there is no current flow and galvanometer shows 0 deflection. Mark this voltmeter and ammeter reading. Okay. Due to lack of mechanical equality between the two strips, the experiment is conducted again. This time B is exposed to sun's radiation and A is heated using electrical current. Now again we will get another voltmeter and ammeter reading for 0 deflection of the galvanometer. So average of these values are taken. Average values of current I and voltage V are taken for null deflection. Now heat energy produced by electric current per unit time is P. Let it be P. So P is equal to IV, where I is the average value of current and V is the average value of voltage. Then the amount of heat absorbed by the strip exposed to sun per unit time is alpha SA, where alpha is the absorption coefficient of the strip. Then S is the observed solar constant. Then A is the area of the strip. Now when galvanometer shows null deflection, this P is equal to this value. So P is equal to alpha SA. Now this alpha SA is equal to IV. So from this we can calculate the value of solar constant. Our observed solar constant is IV by alpha A. So, I have already told A is the mean area of the strip exposed to sun, alpha is the absorption coefficient and S is the observed solar constant. The solar constant determined using this equation has to be corrected for the absorption by the atmosphere, because the sun rays incident on the Earth's atmosphere, all the radiations are not accepted, or are not allowed to pass through the atmosphere, because the atmospheric contents will absorb part of the solar radiation. For this, the solar constant is determined for different elevations of sun on the same day under same sky conditions. So let S naught be the true solar constant. Then it can be shown that S, our observed solar constant S, is equal to true solar constant S naught times tau raised to sec Z. Tau is the transmission coefficient of the atmosphere, and Z is the zenith distance of the sun. The zenith distance means here the angular distance of sun from the surface of the earth. Now taking logarithm of this above equation, this is of the form log AB. So log AB is what? Log A plus log B. So we can write log S is equal to log S naught plus log tau raised to sec Z. C. Now this term is of the form log A raised to M. Now it can be written as M log A. So log tau raised to sec Z in our next step becomes sec Z log tau. Log S is equal to log S naught plus sec Z log tau. So on rearranging this equation, log S is equal to log tau sec Z plus log S naught. Now this above equation, this equation is of the form y is equal to mx plus c, which is the equation for straight line. So on plotting values of log s on y-axis and sec z on x-axis, a linear graph is obtained with y-intercept log s naught. So this is how the graph will look like. This is the y-intercept. This point is 0 log s naught. This is log s plotted on y-axis and sec z on x-axis. Now from this log s naught we can find the value of s naught. S naught is equal to, what is S naught? S naught is a true solar constant. S naught is equal to 1340 watt per meter square. Next we have to find temperature of sun. The term temperature of sun stands for surface temperature of the sun. Let E be the radiant energy emitted per second per square meter by the sun's surface. So that is the emissive power of the sun's surface. By Stefan's law, E is equal to sigma into T raised to 4. We are assuming the sun to be a perfect black body. So T is the black body temperature of the sun, and sigma, it is a Stefan Boltzmann's constant. Its value is 5.67 into 10 to the power minus 8. I had already told in my last video. Now in my previous videos. Let Q be the total amount of radiant energy emitted by sun's surface per second. Now capital R is the radius of the sun, and so Q can be written as sigma T raised to 4 times 4 pi capital R square. So this is the amount of radiant energy emitted by the sun's surface per unit time, per second. Earth revolves around the sun in orbit of average radius r. Consider a sphere of radius r. Imagine sun is on the center of the sphere and earth revolves around sun through the surface of the sphere. This is how the picture will look like. See, the sun is on the center and earth is on the sphere, on the surface of the sphere. Earth revolves around the sun. The radius of the sphere is r. It is the radius of the earth's orbit. Okay. Now the energy received per second by sphere of radius r, small r, is also equal to Q. This Q is equal to 4 pi r square times S naught. What was S naught? S naught is the true solar constant. So the energy received by the sphere from the sun is uh, 4 pi r square times S naught. Now these two equations are equal, so we can equate the RHS. So sigma t raised to 4 times 4 pi capital R square is equal to 4 pi small r square times S naught. See, now from this we can calculate the temperature of the sun's surface. Temperature of the sun's surface is r small r by capital R the whole square times S naught by sigma the whole raised to 1 by 4. Now this is how we calculate the temperature of sun. Now temperature of sun can also be calculated from Wien's displacement law. Lambda m into capital T is equal to into the temperature is equal to B, where B is a Wien's constant. Its value is 2.89777 into 10 to the power minus 3 meter Kelvin. Now this temperature is also called color temperature, and lambda m is the wavelength corresponding to maximum emission. So that's all for today. Thank you. If you have any doubts, please comment on it. Thank you.